All right, so we're going to be looking at, well, they call it optimal outcomes. We'll go with that for now. Optimal outcomes. And this is kind of neat the way it works. And what we're going to look at is a really super incredibly simple example of this type of math. Because they get really quite a bit more complex than this. And really, what it is, I don't know if you've ever heard this term, it's called linear programming. Right? And at its very core, linear programming is just solving a system of inequalities. Okay? Solving, in its simplest explanation, a system of inequalities. All right? And in the sense of a business, right, in the context of we're operating a business and making things and selling things and making and selling more than one item, right? And so what happens is with this, so each inequality is what's called a constraint, okay? Each inequality is a constraint. Okay? And these inequalities will set up sort of the boundaries within which we want to try and optimize some other function, like maximize profit or minimize expense, right? Okay? So we'll talk about optimizing. Okay? That's maximizing revenue or profit or minimizing expense. Okay? So maximizing revenue / profit. And of course, if you're talking about expense, to optimize that, you're talking about minimizing expense, right? Minimizing expense. Okay. And we're going to get into, like I said, this real simple, dip your toe in the water here. It's going to be no more than two equations with two variables. But, you know, so we're assuming a business that makes two products only, right? So you could imagine some businesses out there make thousands of different products, right? Each has their own set of constraints, whether it be how many hours they can allot for labor costs to make things, machine time to make a certain product, right? Things will have to be less than or equal to the total number of hours you can dedicate your workforce to it. Does that make sense a little bit? And it's within that you find where you can maximize profit, right, with what's called an objective function. Okay? So your objective, you know, your objective function could be an equation for profit, P equals whatever, you know, depending on how many things you make and sell. And you're trying to maximize that objective function within the constraints of your inequalities, okay? And we'll be able to look at this graphically because it's only going to be in two variables, right? X and Y. So you can imagine if you get to more products and more things, you're going to have dozens and dozens of variables, and we don't have enough axes on any graphs to do that. We could go to X, Y, Z, right, in the three-dimensional plane, okay? But when you get past that, then you got to start just like trusting your mathematical instincts. Has anybody ever heard of linear algebra? You've heard of linear? Okay, so linear algebra is a branch of math that just deals with solving linear equations. And they use matrices, and you reduce, you know, row-reduced matrices and reduced echelon form and all that. And someday, if anyone goes on to study math, they might run into that, okay? Sounds simple. Still, linear equations are easy. Well, not once you give it its own designated name for a concept and then spend the entire college course teaching. It's not that simple. All right, but anyway, let's just look at an example, okay? So let's go to example 1. Okay? Over on page 591. Can you see that? Read just, let's see here. Casper, read that, will you, about this Trax Corporation?
Yes, I will do that.
Wonderful. 591, I think. I can see it.
Yeah, I was on that page.
Yeah. Wonderful.
Trax Corporation makes running shoes. It has 2 of the best-selling brands on the market, Elite and Bolt.
Okay, let's stop right there. So we have 2 shoes that they manufacture, right? And this is so simple, right? They're only making 2 different styles. Elite shoes and the other one's named Bolt. Go ahead.
Shoes are assembled at their warehouse by machine and then finished by hand.
Okay, hold on. Okay. So each pair of shoes is partly made by machine and the other's partly made by hand. Okay? So you have machine hours you can devote to these, and you have labor that you can devote to these. And I'll bet there's a limit on the machine hours and the labor that you're willing to devote to it. Go ahead, Casper.
It takes 0.3 hour for the machine assembly and 0.1 hour for the handwork to make 1 pair of Elite. It takes 0.2 hour on the machine and 0.4 hour by hand to make 1 pair of Bolt. Since Trax makes other products at their manufacturing plant, they can allocate no more than 900 machine hours and no more than 600 handwork hours.
Okay, does that, what he just said there, no more than 900 machine hours and no more than 600 handwork hours, right? Does that sound like constraints?
Yes.
Does that sound like something has to be less than or equal to those things?
Yes.
Does that sound like 2 constraints? And do we have 2 variables?
Yes.
Okay, so 2 equations with 2 unknowns is very solvable, right? Like if you have 2 variables, to be able to solve the system, you must have 2 equations. If you have 3 variables, how many equations do you need? 3, etc., right? The number of equations has to equal the number of variables if it's to be solved, okay? So let's do that. So they're talking about letting x equal 1 and y equal the other. No. So how about we do this? How about E equals the number of Elite made? And it might be handy to use B for the number of Bolt made or manufactured. Okay? So let's think about the constraints in terms of, say, an inequality. And let's think about the machine hours first, because they listed that first. Okay, so for machine hours, we're making E number of elites and B number of bolts, okay? So each elite requires how many machine hours to make? 0.3. So you would think that for every elite, we got to multiply that by 0.3 for the machine hours, right? Okay, so this would be 0.3 E. But we're also making bolt in the same machine, right? So what are we going to add to that? Because bolt was 0.2 machine hours for bolts, 0.2 times B. And what's the max amount of machine hours they're willing to dedicate to it? Okay, so what do I write? What would I write? Less than or equal to 900. All right, you got your first constraint, right? All right, so then hand hours. Maybe you're getting the idea now. What would be the inequality for hand hours between the 2 of them? 0.1 E, 0.4 B, less than or equal to 600 hours. There we go. Okay. Now, since we are operating in the real world, will they ever make a negative amount of elite or bolt shoes? Okay, so as you know, we're going to be operating in quadrant 1. So there's technically 2 other constraints here, are there not? Okay. How about the number of elite produced? What would be the constraint on that? So E has to be greater than or equal to 0, right? And Bolt produced. What would be the constraint? B would be greater than or equal to 0. They can make 0 to however many, right? Not negative is the idea, right? And it sounds obvious, right? But as a technical matter, this is another constraint, okay? So we have two equations, two inequalities, right? And the other two here. So we're going to graph these on our TI. And the way I want to do it, I'll just make a quick sketch of it here. So, and I'm going to use, and it almost doesn't matter, for the x-axis, I used the elites. So E will be our x and we'll make B. It really makes no difference in this case, right? Because one isn't the input to depend on the other, right? Now, what they have not given us in here is the objective function, okay? We'll talk about that in just a minute. So let's go ahead and graph that. So what do you think our window should be? Let's think about the window for this inequality. Like, if that's our x-axis, how do we find like where it hits here? I mean, you know it's going to be one of these, right? It's going to go like this. So how would we find where it hits the e-axis? What do you put in for B? 0, right? And you got 0.3 E, right? So you'd have 0.3 E equals 900, right? Divide them both by 0.3. What's 900 divided by 0.3? $3,000, right? And so maybe you want your window for the x-axis, in this case the e-axis. I want to have just like, when it comes up on my calculator, I want a little bit of space, like in the negative, just to see, right? Get a better picture of it. So I might say negative 500 less than or equal to E. Well, we'll call this our, anyway, it doesn't matter. And maybe I'll go out to 3,500, right? How high should I go? What's 900 divided by 0.2? Yeah, 450. Let me think of it this way. Yeah. It's going to be bigger. $18. Now let's try. Well, what about the other one? What would be 600? Try this one. 600 divided by 0.1. Is it 6,000? Yeah, it's got to be. So maybe we should go out instead of that one out to 6,000. Right? You might want to check them both. See, like one of them is going to be way out here, another one maybe not so much. Okay? Yeah? So you get this, the idea how to think about the window now? Right? So let's try and graph this thing. Put your TI. All right. And so you want to be able to enter these as a relation, right? I'll just do this one here. Okay. Let me get the window set in first. Okay. You see that? So on the x, so 900 divided by 0.2 is 1,800, right? 1,800, right? No, not 1,800. Sorry, stretch that. I just want to double check. I told you I'd be fumbling with this a little bit. It's been a while.
I think it was 3,000.
Yeah, that's what it was. So 900 divided by, what is 900? divided by 0.2,
I thought it was 0.3.
no, 0.2. So 4,500, that's what we really gotta get out to. What do I have on the thing? And what's 600 divided by 0.2? So we might want to go up to 5,000. That's what we probably want to go up to, 5,500. I don't know where we got, maybe we got 3,000. Check that again. What is 900 divided by 0.2? Oh, this is for the top. So, sorry, this is for the top. I got that wrong. So if I'm dividing by 0.3, right, means I put a 0 in for B, right? Okay, and then the upper one would be, right. I should have left it as X and Y because then I wouldn't get so confused. This is probably the only downfall to making your variables look like something that's special. All right, so that'll be that way. Let's check it this way. Hang on. Let's do this. So the E-intercept, let's do it this way. So the E-intercept is where B is 0. 900 divided by 0.2 is what? That's 4,500. What is it down here? The E-intercept. It's 900 divided by, or 600 divided by 0.4, right? Right? What do you get? Divided by 0.4 gives you what? Huh. Takes you that long? 600. I don't even trust you now. It took so long. Divided by 0.4. Okay, 1,500. I should have trusted you. And now let's do the two B intercepts. So then it would be, that'd be 0. So what's 900 divided by 0.2? 0.3. 0.3.
We're doing B intercept now.
Now we're doing the B intercept. Wait, what did I do here?
You just did it.
We're in section. We're on different things.
You got it right.
So is that my E-intercept where B is 0?
Yeah.
And this should be 0.3.
Yeah, because
That's what it is. And what do we get? That's all right. Hey,
Just change that to your.
we'll get this. Because they don't feel like it. 900 divided by 0.3 is what? 3,000. Okay. And did I do this one right?
no,
The E is where that's 0. No, so that's got to be divided by 0.1. Jeez. And what do you get there? 6,000. Sure about that? Okay. Doesn't matter. The B-intercept. Now for this one, that 900 divided by 0.2 is what? We're on it now. That's 4,500. And the other B-intercept is 900 or 600. Jeez. Yeah, it's a good thing I came into work today. Divided by, so we put 0.4, and what do we got? 1,500. So this is the B-axis. We should go from 0 to what? Or negative 500 to what? Let's go out to 5,000. And what's the biggest E-intercept of the two? Probably that number that's bigger, 6,000. So maybe we'll go from negative 500 equal to E less than or equal to 6,000. There we go. All right. So this is like the Y, and this will be like the X. Okay. It was 6,000, you said? Maybe, so 6,500. Let's make it 6,500. Okay? So that's what we use. So X 65 and Y. Now let's try it. Okay. Windows Zoom. 02, and we said what for the X? 65? 6,500 for the X?
Yes.
And for the Y, we went from 0 to, say it, is that right in front of me?
5,000.
Oh, I didn't want to do 0, I did say negative 500, right?
I just adjusted my.
I did say negative 500, negative 500. So this is what I want, you got this, guys? Now try it. There we go. Woo. All right, let's start putting our relations in here. Which I know sounds.
Well, it can be, it just can't exceed. Can't exceed. We can't exceed.
So I don't know if there's a shortcut to the, like, if I do menu and then graph edit entry and 2, is there a quick way to get to that?
Wait.
Menu, graph edit entry, and then relation. Now remember, the E is our X. So 0.3 X plus 0.2 Y.
It's not that.
And we need less than, so you do like control equals, right? 900.
You don't have to overanalyze every single thing that goes on. So don't.
And then the other one is 0.1 X plus 0.4 Y plus enter equal to 6.
Oh, this is not fun.
Okay? Now, I'm not going to bother putting in the greater than 0 for both of them, because if you do that, then the shading gets out of control on there. It starts to clutter up. Okay? You guys with me? Am I going to put in the X greater than 0 and Y greater than 0?
You just said you weren't.
But I know, but it's for those
Why didn't I get
primates back there.
what that is?
And why don't we go ahead and get this crap out of the way? So, delete, just in the way. All right. So it's all less than, right? So do you see this region? So it's bounded by all 4 of these constraints, right? And this shape right here, this quadrilateral, that's called the feasible region. So any combination of X and Y, or E and B in here, coordinates, right, will make us money, some amount of profit. But what you want to do is, like, our objective function will be profit, and it'll be a line, right? And as you slide, like, maybe your pencil across here, you're going to hit one of the 4 vertices of this thing last. Okay, that makes sense? And that is where you optimize your profit. But if you want to minimize an expense, you'd slide like the last one you hit going this way, right? Okay. So let me just make a sketch of that. In fact, maybe I'll just put that in. I can do, what do I do? Comp screen capture. Yeah, like that. And I'll just put it in here. Paste. That. Okay. So you could just make a quick sketch of this in the graph we started, right, roughly, okay? So this region, that quadrilateral that's bounded by all four of those constraints, okay, this is called the feasible region, right? Huh? That's this region right in here. Okay? Anything in there, given our constraints, is a possibility to make these two pairs of shoes, right? But we also have four vertices here, don't we? Here, 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 and here. And it's one of those vertices that's going to optimize our profit, right? But what you need to do is actually have the objective function, which we don't quite have here, right? So what we need to do is find the coordinates of these vertices, right? Well, this one's easy here, right? It's 0, 0. And probably once you get this in your calculator, the best way to do it is to use the trace feature, maybe, and then the intersection, okay? So I would say use trace / intersection to find vertices, the coordinates of them. And one of those four pairs of vertices is we're going to optimize our objective function, which we don't have here quite yet. We will in the next example. So let's get these. That's 0, 0. So let's go here and trace this guy. So menu, or we could find, yeah, well, that's one way to do it. There's another way probably. 5, enter. So anyway, well, that's perfect, right? We already kind of found that with one of our windows, right? So the coordinates of that point are 3,000, 0. All right, so this one here is 3,000, 0. Let's go to the other one and trace and come back and find the y-intercept. Of course, we already did that too, right? Where's my calculator? There it is. Let me just move up. I'll just go all the way back here. Faster to do that, or come on. Let you guys know a quicker way. Or the intercept. Oh, okay, y-intercept, yep. So that's 0, 1,500, right? That's E, comma, B. Like making 0 elite and 1,500 bolts. So this is at 0, 1,500. And what about the intersection there? We could do trace, or we could do a different thing. Okay. Stay out of that. I'm going to do it this way. Menu, analyze graph, and do the intersection for what? Finding the intersection. Lower bound, upper bound. 24, like he said, comma 900. Right? And so this is at 2,400, comma 900. Right? So where they intersect, you would make 2,400 pairs of elite and 900 pairs of bolts. Okay? So our optimization is at one of these four vertices. I don't know, you think it's this one, 0, 0? It's hard to optimize if you're not making a damn thing, right? All right. Well, anyway, that's the setup. So we don't have an objective function, right? I think they're going to give us a profit function in the next example. And I'm going to kind of combine examples 2 and 3. I know I bumbled around when I told you I would do that here. But is there anything here you're not understanding about how to get it? We have limits on machine time for each, right? And hand labor time for each. And we also have a constraint on everything being positive, so quadrant 1. But again, I wouldn't put the constraint inequalities here, because then like the overlap of shading would just be so blisteringly mind-boggling to figure out which part you want to look at, right? Okay? Anyway, let's go to example 2, because then they're going to give us some things here. Well, actually, I'm going to do kind of 2 and 3 together. Because 2 in itself, I think we could manually check something. Oh, they found the vertices, basically. So we kind of did example 2 already, right? Okay. Let me give you a quick, let me do this first. Let's talk about what the objective function is real quick. Make sure you're clear on that. So what we've graphed here, by the way, this thing that we graphed is not really our function that we're trying to optimize. This is the boundaries for the function we want to optimize, okay? So once we have these boundaries in place, we will need, how does that work? An objective function, huh? Is what? Which part? They're all relations. Right. But by the definition of the word, I mean. So objective function. Okay. So that's the function requiring optimizing, max or min, right? Okay. This is the function requiring optimizing. Okay, max or min, depending on what it is. You certainly don't want to maximize expense, right? If that's your function. Okay. So you use coordinates out to the right for max, and it'll be to the left for a min for the most part. Okay. So that's our objective function, which they did not give us. So we had no function in example 1. All we did was graph the constraints. Okay? So now we're going to, okay? And I think 2 goes and finds all these coordinates. So we have all those. So let's jot these down. So we have 0, 0, and we have 2400, 900. Let me just go in order around. 0, 1500. Yeah. Yes. And then it was 2400, 9000. 900. And then it was 3000, comma 0. And remember, this is E, comma B for all of them. Okay? E, comma B for all of them. Okay. So now, if we look at, let's go right over to example 3. They've determined that they make a profit. So they went through the thing, right? So this is not going to be quadratic. What they did is they found that they probably used their function for profit and they got a quadratic, right? And then divided the total profit by the number of things that they make. And they make a profit, or actually what they're doing is just doing their wholesale, plus markup kind of thing, right? Like if they make it, it costs so much, they sell it. That makes sense? So they make a $20 profit on the elites and $30 for bolts. Okay? So the profit function, the objective function would be profit equals $20 of profit for every elite, yeah? Plus $30 of profit for every bolt that they make. And it has to be within those constraints, okay? Hello, Sheldon. This is our objective function. All right? This is the thing that we want to optimize. In this case, do you want to max it or min it? Good call, because it's profit, right? So what we have to do is take all the possibilities for optimizing this are of these 4 pairs of coordinates, right? So what you have to do is check each one of those in here. Remember, they're E, comma B. So obviously, at 0, 0, you get profit equals 0, right? Let's try 0, 1500. 0, comma 1500. Profit equals 20 times 0 plus 30 times 1500. Is it? 40, 45,000, did it say? What do you got? Oh, because that first one's here, yeah, so it's 45,000, yes. Thank you, Sheldon, man, wasn't ready for you to be. So that's the profit at that vertex. What about at 2,400, 900? So that profit would be 20 times 2,400 plus 30 times 900. What do we get for that bad boy? 75,000. 99. And the other one at 3,000. So 3,000, comma 0. You get P equals 20 times 3,000 plus 30 times 0. So it would be 60,000. Okay? So those are the four possibilities for optimization. It puts you right up against the edge of all those constraints. That makes sense?
Yeah.
Right? Like, it can't just be like somewhere along this side of the quadrilateral, right? Because you're not up against the edge of both the constraints of this one. You're up against only one of them, yeah? You're not making full use of the other one. You get what I'm saying? So it won't be anywhere between the vertices. So again, because if you're trying to find a point in between the vertices on one side of the quadrilateral, you are not up against both constraints. The only way to do that is to be like that, right? Or all four constraints in this case. Okay. So which one of these makes us the best profit? Okay. Right here. Okay. So max profit, making 2,400 elites and 900 pairs of bolts. Huh?
They sound like garbage.
Do they? Oh, same bolt?
Yeah, there's something.
Elite sounds like garbage? Or maybe you should rename it, just call it garbage.
Yeah.
Yeah, this is our garbage line.
No problem.
Yeah, you'd find it ironic that you just have to have a pair, wouldn't you? Yeah, I think I
And
would.
they turn out to actually be pretty confused.
Huh?
Price for garbage.
Yeah. Well, this is all gonna be online, so we need to keep, online. All right, so you kind of get the idea. I know it was a little fractured and scattered there, right? Okay? When you graph them, I would say definitely make your window. I like to have a little bit to the left and below it just to see. We're not going to use that, but it's just like when you're trying to find points out there, right? It's a little easier. Okay?
Now, when they give you the 20X and the 30Y, where did they get those numbers from?
This here?
Yeah.
That was it. So they if you read it, it just said this is what they know they're going to make $20 for everyone. So they know what they're going to sell it for, and they know what it costs to make one, right? Pair, and they just subtract them. Okay? So it's not quite like the quadratic profit function we've been looking at, right? It's in a different form. All right, let's go. I think there's one more example I want to look at. Example 4. Paul, let's read example 4, would you? Not on track. Way over. Oh, no. Oh, yeah, no. Yeah, down the bottom. Go ahead.
To-go cup is a small business that makes two types of plug-in temperature control beverage containers for home and auto use. To-go hot and to-go cold. As the name suggests, to-go hot will continuously warm a beverage to a set temperature, and to-go cold will keep a beverage at a continuously cool temperature setting. Now, the cost for manufacturing is $25 each. The to-go hot and the to-go hot
$25 each hot.
and
Very good.
it's $25 each for to-go hot Oh, okay.
and $30.
For to-go cold. Nora and Anthony are the same, are the company, actually. Nora and Anthony are the company owners, and they have found that a local retailer who has agreed to promote and sell all to-go crop items in the store for a trial period of 2 months. The retailer will continue to take an initial shipment of the most 500 items combined. The agreement is.
Well, hold on, right, does that sound like a constraint? Okay, go ahead.
The agreement is that at least 200 to go hot and 150 to go cold must be sold during the 2-month period.
Do those sound like lower bounds then?
Yeah.
A minimum, so not just like above 0 for each one, right? Like the last one? So we'll have it there, so those we probably want to put in the graphic calculator since they're not 0, okay? Well, did you finish reading?
Pallets of each type must
Yep.
be made and sold.
Okay. So in the beginning of the paragraph, they kind of gave us the objective function. What is it they want to optimize here? Profit, cost, revenue, what? Nope. Read the last sentence, I guess, then. Minimize costs. So can we write an objective function for what we want to minimize? The objective function will be cost, right? Right? And what we want to do is optimize that. In this case, we want to minimize it. Right? So let's write the cost function. I don't want to use X and Y. Cost equals what? For both of them. And we add it together. So let's use H for the hot one and C for the cold one. What is it? Oh, yeah. Maybe we'll call that expense. What can we name? We don't want to use. I guess we use lowercase c, whatever. So, okay. Nah, come on. What's the cost for the hots? So what do I write? 25 H plus what? $30 for every cold one made, right? This is our objective function. That's what they didn't give us, right, in example 1. But now we have some constraints. What's the first constraint?
No more than 500.
Okay, no more what?
To go or to
Between the two of them, total together 500. What would that look like as an inequality?
greater, less than.
H plus C less than or equal to 500, right? What was the next constraint? Is there a minimum number of hots that they should make?
200.
So that would be H greater than or equal to 200. And what's the other one? 150. Okay? So let's get our constraints plotted. You with me now? You figure out how to get the constraints now? Okay. So let's clear out our window here. I'm just going to give you the, so let's do this. Let's do window, so we don't even need the negative part. How about 0 less than or equal to H? Let's go out to 500. And then 0 less than or equal to C. That's going to be our y-axis. Less than or equal to, let's go up to 600, I think. All right. So this will be the equivalent of our x, and this will be our y, so we don't get confused. All right. So let's put our constraints in here. Change our window first. Let's get everything out of the menu. Clear actions 1, all 4, first, right? Menu, window zoom, Zero, what did I say, 0 to 500?
Yeah.
Yeah.
And then 0 to 600. Let's put our relations in.
Okay.
So, do x plus y total equals less than or equal to 500. And x greater than or equal to 200. And y greater than or equal to 150. Oh, okay. Oh, whoops, daisy. There we go. Oh, let me get this stuff out of the way. So if I come over here, delete, just, I want it out of there. I mean, you can leave it there if it doesn't bother you. Delete. All right, so do you see our axes are here? And do you see where our feasible region is in here? Right, so it's not down here like it was on the other one or over here. It's in this triangle now. Okay? So we'll need some vertices for that. Let me just, I'll throw this in. Window, no, tools, screen capture. Yep, put it in here. Edit, paste. Yeah, that. You can just feel free to make a sketch because I'm better than you. All right, so there is. So this here is going to be our feasible region, right in here. I'll put an F in here for feasible. Maybe I should do that red or something. Okay, that's our feasible region. Maybe I should do it. Huh? Green, maybe, yeah. Let's see. Oh, yeah. There we go. So whatever we choose has got to be somewhere in that region or on one of the vertices, okay? So let's find these three vertices here, okay? And I think we could just do a bunch of intersections here, couldn't we? Right, so let's just go back to our calculator. So menu, analyze graph, intersection 4. And we got to figure out what graph we're on here. How do I do that? Up and down?
Just click the graph.
Oh, okay. So let's do like that guy and that guy. I don't know.
Since there are two intersection points,
Yeah.
have to make a box.
Is that what you got to do?
Yeah. You
Oh,
make a
yeah,
box
remember that.
around it.
Like this?
So
Wait a minute.
just click somewhere around it, and then you make a box over it.
Yeah. Oh, I see. Oh, escape. I should have clicked off it and then draw.
Yeah.
I see. I got you. I forgot. I remember doing that a couple years ago. Now that's one you don't use that often. So menu 6, 4. Well, you guys are masters at this. So that one and that one, and then click. Drag it down here. That. Okay. So that is 200 comma 300, right? So this one here is 200 comma 300. Let's find the other one. darn it. So, menu 6, 4. Now I want to do maybe like this one, and this one. Now now it's doing lower bound, okay.
It probably because one of them was completely vertical.
350 and 1, yeah, you're right. 350 comma 150. So this one is at, right here is at 350 comma 150, right?
That was 200, 150.
And this one is 200. You guys are tired of waiting for me, aren't you?
Well, you could just read it right there.
All right. So now we have to test these points out in our objective function, right? And we want which one? Not the max, but the what?
The least cost,
Okay.
the minimized cost.
All right, so let's start plugging these in here, right? So maybe the 200, 300. So C equals 25 times 200 plus 30 times 300. What do you get there? 25 times 200 plus 30 times 300. No way. Wow.
No, that's tight, right?
I don't think so.
Not even close to
If it is, we better find another business, huh? 25 times 200, maybe I didn't hit the plus 30 times, oh, so it's doing it, I know why. This is different. Yeah, I know, I could have done it in my head by now. But now it's like, so 5,000 plus 9,000 is 14,000, right? You guys get 14,000 here? Let's try the other one, 350, so C is 25 times 350 plus 30 times 150. Just do it this way. 25, 250, 30, 150. 250 plus 30 times 150. 10,750. No? No? What is it? Just tell me. I'm tired of missing buttons up here. 13,250? Okay. And the last one. The 200. So that's 25 times 200, right?
Yeah.
Plus 30 times 150. And what do we got there, guys? 9,500? So we should go with the 14,000, right? No, this is cost. We want minimum. That's the min. So given the constraints, and that being our objective function, right, we find the minimum cost making 200 hot and 150 cold.
But does that really mean they're making a?
No, that just, no, right, good question. Because nowhere in here was a profit function to optimize. We were just optimizing cost, right? I guarantee you that if there was a profit function in here, then we'd have a different set of things probably, right? Maybe not, I don't guarantee it, maybe not, okay? But you're right, it doesn't guarantee the max profit. Okay? You get that? I bumbled around a little bit, but.
Yeah.
So like if you see one in the homework, maybe let me go back to the notes, watch the video. I'll stop it.